Okay, let me get my microphone. Okay, let me get started. I'd like to start off first by going over everybody should have gotten back their project progress report grades, right, and comments, right? Okay, so what I would like to start off with is to do some kind of a presentation of how, what were the major conclusions after, or major comments after people had, in grading the progress reports. First, these were the results. I worry about a couple of things. I worry about do the TAs and the peers grossly agree? And on almost all the projects, there was a good correlation between the scores of the TAs and the peers. The one project where that wasn't true was on the retrieval patterns, where actually there was an inverse correlation. The one the students thought well were the ones the TA thought badly. So for this one, I read all the projects also, and came to there was a third judge on this one. And in this case, that's a small project. All the teams were actually not that bad, actually, compared to, it was a somewhat better distribution than the people that were, on the other project that I graded. And there was some judgment difference. So, in this case, we added a third one. Mine correlated well with the, with the TA, and, positively, but weakly positively with the students. So, but we've done, we treated those grades appropriately. This was the distribution of scores over the whole class, as you would expect because of the Z-score type thing. We have a bell-shaped curve centered around 0, and so the distribution looks right. Any questions about these scores here or in TV land? Okay, now as far as the general comments, actually I realized I didn't put these comments on the website yet. Somebody sent me email to remind me of that, to put that on the website. But what were the comments? First, there was one DA put together a list of general comments. One thing that's going to be true for the final one: stay within the page limit. A few people try to exceed the page limit. Generally, I don't see a reason why. It's not like they had more material than other groups. It's not like, so it's important to stay within the page limit for the final. One thing that many groups try to do is they try showing us a lot of different methods and stuff like this. Running the things, if you're building a classifier, they use a library call and run it through a lot of different algorithms. The things that make for the more interesting projects, or when you're doing a better evaluation, I think I agree with that, a better analysis of what your data set is like, some kind of a novel task, okay? These are often better projects. Again, if you do implement several different models, you might want to try to explain what the difference between the results is. So it's not just, we don't just want a table at the end, we'd like to know why. Again, it does pay that the paper be well written. And, certain things like spell checks and proofreading and stuff like that's a good idea. When you have a well-formatted paper, typically you have section numbers, table numbers, figure numbers, so you can refer to them. and that's a good practice. Any questions about general comments? Okay, so again, we had every TA also make up a slide of specific problems that they had. So the circadian rhythm one, which is one that I read, one thing that that was true is many groups, showed graphs, made big claims, but they didn't generally do statistical tests to validate something. If you're going to tell me something like students sleep, that bartenders sleep later than school teachers, okay, we should have a proof of that. And the proof of that is a statistical significance test. A lot of people made up curves where they were showing me the behavior, the sleep cycle of different groups. And they would be students, and it would look something like this. And then there would be presidents, and it would look something like this. And that's because they're showing counts and not normalized counts. And so it was impossible to really tell if the same thing is going on or not. A lot of groups complained that, oh my God, this is a big data set we have. We want to use these APIs. And, but we don't have enough time to do it for all the data set. Or we don't get enough calls to the API to do it with the entire data set. Well, then there is a reasonable question of, how do you live within a resource constraint? Okay. The wrong thing to do is just take the big file and start from the beginning and see how far you get. A better thing to do is maybe to do some pre-processing of the file. If you want to find out what locations are, well, if you counted the locations beforehand, how many times each one had occurred, you'll find there's more people who came from New York than came from Poughkeepsie. And being able to figure out geolocate New York is a more powerful thing. And, that's one example. Or the idea of using stratified random sampling so that you get a certain number of samples from each pool seems like a good idea. And again, I think that, a few people started looking at the largest data set. I kind of like that. That's where you have a lot of different titles. So the thing that seems most exciting to me, personally, is something about seeing how the titles differ. Okay? Is it true that bartenders are different than baristas? Is it? And some of these titles may kind of mean the same thing. Okay? And, I think that looking at that would be a good thing. Any questions from anyone with the Twitter project here or in TV land? Okay. For the job title data set, some groups, okay, good. This is the midterm, right?
Oh, yeah.
Great. Okay, thank you very much. Okay, that's not the midterm for this class, so don't worry about that yet. But you will have a final, and we'll talk about that after Thanksgiving. Okay, what else do I know? With the job title database, some people kind of presented purely visualizations, and didn't start thinking about models. One thing that he was complaining about is that some people didn't have really clear direction. Okay, it's important to try to find a direction and move in it. Okay, again, I didn't read these, but I think that may be a source of problem. Any questions on the job title one? Okay, for the sales pattern data, retrieval from sales, one thing that I noticed is very few of the groups were actually working on trying to order what would predict the order of the items in the baseline, okay, in the basket, which is what I think is probably the most interesting question. There was only, I think, one team that did something meaningful there. So if you're asking me, okay, I would be saying that trying to predict what the order of items in the basket is a very interesting thing. And I mean, the simplest thing to do is for every object, okay, figure out where it is on average in the basket. If you took for anybody's shopping basket, if you put the item in, it's either in the first, the first position, second. If there's n items in the basket, any particular item has a fractional position in the basket, perhaps the average, the position over n, okay, for the items in it. I guess we should have a quote here. And it would be interesting to know which objects are overrepresented early in the basket, which objects are overrepresented late in the basket. And is this a statistically significant thing? I still claim that there's ordering information there. And once you look at once you really look at what objects are unusual in a statistically significant way, you could probably start to get a handle on this. A lot of people were trying to build embeddings of the items, but the way I saw it, a lot of them seemed to be trying to use word embeddings as a way to do it, which is fine. But the words that they were using was what words were like, what group was it in, what subgroup was it in, and that they kind of formed a sentence of the form, what was the group ID, what was the department ID, what was the name of the product. Another way to do this would be, what if you had for every basket, you construct the sequence of the items, item 1, item 2, item 3, item 4, just the order, just the items that were in each basket. Now you've got a sequence of items from each basket that represents a string where on the vocabulary IDs, each item has an ID associated with it. And then if you did the embedding of these kind of sentences using word embeddings, I think you will find that the items kind of capture important things, okay? And I think that might be something that's kind of interesting to play with. Now, many of people are instead started treating this, not the order of the items, but they were interested in what items are sold with what other items. This is a classic, what do we call it? Not data mining. What do we call it? I think that's a data mining problem. Okay, the trying to determine the frequency with which, or rules under which, that if you buy they determine these association rules. And basically, if you're going to implement it, explain what you're doing. And what I encourage people to do, that he says, that I strongly agree, is sometimes the reports that I read from other places started talking about, oh, we're doing all this pre-processing and then we're going to do our analysis at the end. Well, one is we're getting close to the end, but it's also good to start analyzing things as quickly as possible so you can start to see if there's problems or anything like that. Any questions about the sales pattern data? For the COVID analysis, okay, one thing that the TA said, and that is probably true with a lot of the other projects also, people lovingly describe what libraries they use, and some of the technical processing of how they actually do it. Ultimately, more interesting is, it's important that you do that right, but ultimately more interesting is, what do you actually learn from the analysis of the vaccine data? What other things do I see here? Again, as you try to analyze the vaccine rate, you can look at different things. look at the characteristics among different groups of counties, okay? Because I think that some counties are going to be good and bad at this for pretty obvious reasons. And so I'd like to see that kind of analysis. Now, sometimes people give a model, okay, and they say, look, I got a root mean squared of 6 when I ran it, okay? Is a root mean squared error of 6 good or bad for a model? The answer, of course, is you can't tell. It's a meaningless number in isolation. Now, if you compare it to other models, it starts to have meaning, okay? One being better than the other. But looking at baselines and seeing how a baseline does, how much better are you from a meaningful baseline? That starts to have interesting things. Okay, any other questions? For the flight delay problem, again, what kind of things do I see here? Some people are probably looking at accuracy as a measure. Now, one thing that's true about most planes is that most planes arrive on time, okay? So if you have a model that says that it's always on time, it will presumably give a pretty high accuracy. That's why you want to use, something like F1 or the area under the ROC curve to give you a broader sense of what of how well your model is. Again, some people were apparently trying to analyze weather data, and they found that it was slow to use an API. Do the airports that matter the most first, okay? Do a smaller set if necessary. Some people presumably turned the flight delay problem, how many minutes late will a plane be, into a classification problem. Is it going to arrive on time, a little late, very late? And, you can, when you do that kind of bucketing, you can often come up with, it seems like, there's a lot of things that can be hidden when you take a regression problem, predict the flight delay, and turn it into these discrete buckets. First, the discrete buckets are related to each other, okay? So there is a continuous order on the buckets, which makes it different than most classification problems. And if you make the bins wide enough, okay, then it has very little resolution. Planes desperately want to be on time or close to time, because if not, it's going to, obviously it pisses people off, the customers off. But it causes a lot of logistical problems if a plane is very, very late. Bottom line is, think about doing these as regression problems. I think that's fair. Any question? On the fantasy league, one question is that many teams didn't really talk about how they were going to evaluate their models. They're going to pick a team, they're going to show it. How are you going to be evaluating it? Okay? And it's important that the evaluation be done on a large enough set of data so that there's some statistical meaning here. And that seems to be a problem. My guess is that there seems to here, but number 3, he's complaining that there seems to be some kind of a herd mentality, that everybody is trying to get the best score as you would get on a particular analytics site. If you can come up with a slightly different objective, okay, something more interesting to measure, that's obviously a good thing. Seems that they're using linear programming. Linear programming is a kind of advanced optimization technique. That's good. But it looks like many teams have missing constraints. So my guess is like every team probably needs players of from all different positions and stuff like that, that's probably the kind of thing that may be being neglected there. Any questions? For the segmentation of books, okay, this is a somewhat smaller set of themes, but have a clear description of what you want to do. And if you're trying to identify whether a chapter has multiple genres or something like that, basically, if you have a sensitive enough classifier that's running along the text of a chapter, parts of it are going to see in one genre and some are going to be in another. Basically, the claim is that, we're probably most interested in a dominant chapter for a segment, okay, rather than knowing that it's in multiple such things. Any questions? Okay, any questions about the projects? Okay. If not, any questions in TV land? Okay, so this is back on your plate again. I appreciate the students and the TA's efforts for turning this around so quickly. But now you got the feedback and you can go and finish your project at this point. Any questions? Okay, I am now, let me double check something. Oh my God, no, hold on. Sorry about that. No, sorry. Okay, we've been talking about, I'd now like to get back to the material we were talking about. We started talking about, kind of nearest neighbor methods last class. And, we looked at things like how do you figure out whether or not, yes?
I'm sorry, how long is the final report supposed to be?
How long is the final report? Okay, I took a look this morning. I haven't given you an exact page limit.
Yeah.
I will tell you it will be a number. I will give you the integer. I haven't decided. It will be a number that is either 8 or 9 or 10. So it's not going to be infinitely long. But I may insist that it be shorter than that. Okay? You will not have to give presentations. Okay? That's the other question here. The class is unfortunately too big for that. Okay? Any questions about that? Okay, but remind me if by the end of Thanksgiving I haven't given you the page limit. That's a good thing to remind me on Piazza. Okay. Okay, network data. So we talked. Okay, last class we were talking about nearest neighbor search on points. We had records. Records. Individual records could be thought of as a point in, it's kind of, if you have an n by d matrix, you have n rows, which are typically items. You have d columns, which are typically features. And we talked about how you can, we talked about how you can find the nearest point, okay, two rows that are most similar, okay, and, how to interpret that in terms of distances and things like that. Now, there's a class of data matrices which represent networks, okay? Where in a network you can view a matrix as a network as a matrix, where you've got n vertices. And each of the n vertices is going to be connected to a particular subset of other vertices, okay? If connection is 1 and non-connection is 0, you've got each row is just kind of a 0, 1 vector. You could imagine weights based on how similar these things, how strongly connected vertex I to vertex J is. Regardless, networks can be viewed as matrices. And many data sets that we're interested in the world can be viewed as networks. Obviously, Mark Zuckerberg has gotten rich on the basis of networks that are data networks, okay? In Facebook and any other social network, the vertices are people, and an edge represents a friendship. If you're analyzing the World Wide Web, okay, the web pages are vertices, and pages link to others based on directed edges that are basically the hyperlinks in it. Some of you guys are working on sales data. I know some of the people have it. You could imagine a world where you have products against products. I mean, what networks could be drawn in products? You could imagine a world where on one end you've got a customer, and on another side you've got products, and you can have an entry. Did this customer buy this product? That can kind of be viewed as almost like a bipartite graph. We'll be looking a little later on when we talk about clustering at biological data. When you're understanding biological systems, a very important thing are the genes, the things that make different proteins in your body. Certain genes interact with other genes, turning them on, turning them off, being co-regulated. Okay? Trying to understand how a genetic network works. The edges represent the interactions between pairs of genes. Okay? Each row categorizes the behavior of each gene. Any question? So it's quite often that people have network data, and there are certain data science-y things to do with network data. That's a little bit different than, that's worthy of discussion. First thing I'd like to make clear is that there is a kind of a natural correspondence between point sets, like we talked about in the last class, representing, data sets as n rows and d-dimensional vectors, and graphs. So one thing is that there is a way to take a graph, okay, a set of points, and represent that as a graph, okay? Points in space naturally define things that we would call similarity graphs. If we could take 2 points that are considered close enough, maybe we have a threshold, okay? If 2 points are within a distance of d or less from each other, we will add, say they're similar, and we're going to add an edge between them. So it's very, very easy to go between a graph and a set of points and produce a graph, okay? This is the similarity matrix, and then thresholding it, can give us a discrete graph. Likewise, if you have a graph, it's easy to come up with a set of points in another, a certain number of dimensions. If we take the adjacency matrix or some other matrix representation of a graph, if we can compute the SVD of it, okay, we can come up with a d-dimensional representation that captures a lot of the structure of the graph. And so it's natural to move between graphs, between point sets and graphs. Sometimes they're useful to look at point sets as a similarity network. Sometimes it's useful to take a look at a set of points, a network, and embed them as points in a lower dimensional space, so we can do everything that we have done so far with it. Any questions? What is important about graphs? Well, one thing, you guys, if you're computer science students, which I assume most of you are, you went through and learned a fair amount of language of talking about graphs, okay? Knowing that whether your network is weighted or unweighted, knowing whether it's directed or undirected, knowing whether or not it is, sparse or dense. These are the kind of things you should have talked about in a, in various graph algorithm classes and things like that. Knowing what the property of your graph is before you start working on it is kind of an important thing. Is Facebook a directed or undirected graph? Or maybe Facebook is too old for you people. What? Is Facebook a directed graph? A directed graph means that there can be an edge from X to Y that's not an edge from Y to X. Is that true in Facebook? No, I believe, I'm not a Facebook user, so someone would acknowledge, but I think that friendships have to be mutual in Facebook, don't they? Is that right? What about on other in Instagram? Are friendships mutual? You can be my friend, but I don't have to be your friend in Instagram? Okay. So this is one thing that you would want to think of. Facebook, I'm pretty sure, is a undirected graph. Twitter, I know, is a directed graph. People can follow me, but I don't have to follow anybody, right? There's edges of question of whether your edge is weighted. Okay. Is there a number associated with it? In a social network, it turns out that is there a weight associated with how strong our friendship is on any of these social networks? As far as I can tell, no. You could imagine a world where you kind of partition your friendships up. I mean, some of your friendships are stronger than other ones. Okay? And there's questions of whether your graph is sparse or dense. In a sparse graph, a relatively small fraction of possible pairs are connected. In a dense graph, a high fraction of partial what you call it, a high fraction of partial friendships are, available. Which is it true in a social network? Is Facebook or Instagram or Twitter sparse graphs or dense graphs? Sparse. In general, there's 6 billion, umpteen billion people on these networks. You are friends with 100 of them, 200 of them, something like that, right? So a small fraction of these things are done. So learning to look at a graph, there's a language for talking about graphs, okay? And again, it's worth understanding some of these things. One distinction is an embedded versus a topological graph. In an embedded network, each vertex has a position. In a topological graph, it's basically just, connections, and that there's no inherent geometry to this thing. Is a social network an embedded graph or a topological graph? Okay. Let's first start off in the connection between customers and let's say if we took the storage thing where we had the vertices were things you could buy at the hardware store, and the edge was any pair of things that were bought in the same in a basket together. Would that be an embedded graph or a topological graph? Is there a geographic component to that? Okay. Generally speaking, I would say no. Although some of you may say, wait a second, if this is in a store, the items are probably physically bound to a location in the store. There is a place where the bananas are kept in any store. Okay? So you might view that under certain circumstances as having an embedding that matters. But most of the time, it's probably just a pattern of connections. Is a social network an embedded graph or a topological graph? If every person has a location, then actually there is an embedded component to it. It's quite likely that you're more likely to be friends with someone close to you than someone far away, okay? And certainly if you know what the locations are, somehow thinking of that as being a graph that's laid out on the plane can be meaningful and helpful. But if you don't have location, it's just kind of a topological graph. Any questions about that? So it's worth thinking about these things. On the chat, I see that there's a comment that the Facebook graph, the Twitter graph would presumably not be directed, has to be directed, because John Lennon won't follow me back on Twitter. Of course, John Lennon isn't following anybody back on Twitter now because he was shot many years ago. But again, the difference of famous people have a lot of people following them, and they don't follow very many people. Any questions? Okay, so again, the stuff you learn in an algorithms class, I'm not going to dwell on these things. But if you think about what you call it, what some of the classic things you learned in a graph algorithms class, those are things you can do on networks. You can find the shortest path on networks. You can find the connected components. What are the chunks of the graph that lie in one piece? You can find in a directed graph, you can order the vertices based on whether they are sources or sinks. You know, all of these algorithms that you have on graphs, you can apply in a data science way. Sometimes they have natural definitions for things we want to do. What is the meaning of a connected component in a similarity graph? Suppose we have a graph where we have, again, vertices, or let's say people, let's say parts that you bought in the hardware store. And we have edges between parts that are deemed similar. What do the connected components of that graph correspond to? What? Clusters, okay? Does everybody kind of see that you would expect if you had similar things? If you say a nut is similar to a bolt, is similar to a nail, but it's not similar to a hammer, okay? The connected pieces in this similarity graph are going to logically correspond to clusters. And so a lot of the stuff you did in graph algorithms, you know, are naturally good things to want to deal with in network data. But there are a couple of special purpose algorithms that you wouldn't learn, presumably, in an algorithms class, certainly not in my algorithms class. But that do prove to be kind of important operations in data. What is this thing? What is PageRank? Okay, PageRank is a operation on a directed graph that, given a vertex on a directed graph G, it needs to be directed to be interesting. Okay, says what is the probability that a random walk on a vertex, okay, starting from this in this graph, ends up at vertex V. So you can imagine we have a giant graph. We start walking around this graph at random, and suddenly a bell goes off and says stop. What is the probability that you end up at vertex V? Okay? And in principle, it would seem that the vertex that you're more likely to end up on, okay, is probably a more important vertex than one that you don't end up on. Okay? In principle, the idea of PageRank is we would like to have a method that is going to decide something about how important each vertex is in a graph. Now, how important, what would be another measure of how important each vertex in a graph is? If you're given a graph and you want to know how important it is, Is there any other measure you can think of as what makes one vertex more important than another? Its degree seems like a logical thing. Now, in a directed graph, vertices have in degree and they have out degree, right? The in degree of a vertex, the higher the in degree is, the more likely it is that you're probably going to end up there on a random walk. Does everybody see that if you're doing random walk from the graph, if you have a degree in degree that is large, your previous step could have been this, or this, okay? So on one level, in degree should be kind of associated with PageRank, okay? But it also depends upon how likely you were to end up at one place or another. Google came up with the PageRank became famous when Google was invented, okay? Because Google wanted to know how important a website was. And the more points that, the more links you have to a website, the more important that website is. But what was the problem when you measure the importance of a website purely based on how many links are going into it? If, let's say, Google was more likely to recommend your website because it had a lot of links going in, what is a logical thing for you to want to do? Yeah? So you want your thing to be at the top of the Google results because then people will click on it. If Google decides that your web page is important because of its high in degree, what is it that web companies are going to do? You have a web page and you want people to see your product. What is a way that you would go to make more people see your product? Provide a lot of in-degree links. Is there a way to have in-degree links to your product? Okay, how would I increase the number of in-degree links to my product? My page suppose I want to increase my in-degree count of my web page. Okay, ideally the website is associated with my book. I have a web page for my book. I'd love to have that appear at the top of Google. If the importance was purely a result of in-degree links, there's something on the television, create fake pages pointing to that page. Does everybody agree that if I do this, I could set up a bunch of different web pages and have them point all to myself here, okay? If it was just in-degree count, if I'm willing to pay for other web pages that I create, I can boost up my in-degree count. Does everybody see that? Now, PageRank is a little smarter than that, okay? Because what PageRank does is it takes the weight of of all the vertices, the PageRank of all the vertices that point to me, okay? And it's not just a function of how many edges point to me, but it's a function of the quality of the edges that point to me. According to this, what is the idea behind PageRank? It's kind of an iterative formula. We'll say that the PageRank of a vertex V at time j is going to be what? Okay? For all of the edges that point to V, okay, any for edge UV, I'm going to take what is the PageRank of U at time j minus 1. And let's say that I am here a edge, this is V. Let's say that this is U. U has a certain amount of PageRank, and it has a certain out degree itself. At each iteration, every vertex is going to give its PageRank uniformly among its neighbors. Okay? So U has a page rank of 10, and if it has 5 outgoing edges, each of the two, each of the 5 neighbors is going to get a page rank contribution of 2 from you. So what's the important point here? V over here is going to get a contribution for its page rank from vertex U. It is good for me if U has a large page rank, because then it has more mass to give, okay? And it's also good for me if U has a low out degree. If U is only pointing to me, I will get all of its page rank. If, on the other hand, U has a lot of other websites it points to, I only get a fraction, that fraction of U's mass. But basically, my page rank at time J is going to be the page rank of all my neighbors at time J minus 1 divided by their out degree, and I sum that up over all my neighbors. Okay? And if you think about it in a random walk, if I'm going to end up on V from a particular point, the probability of ending up here is a function of the probability that I was at a neighbor of me on my previous step, which is kind of what's going to be captured by this term, the previous page rank, times the probability that if I took a random jump from here, I ended up at U. That's basically, depends upon what the out degree of U is. Okay? So that's why I divide by the out degree. Any questions? What's good about this is that this is a sum that, that tends to converge relatively quickly. So even if you're given a big giant graph, you may start out with the same page rank on every vertex. Maybe you start out with a vector where if you have n vertices, every vertex gets equal weight, okay? Then you go through these operations. The more and more important vertices, the ones with higher in degree, the ones that have important neighbors, okay, will accumulate more and more page rank, but in practice this will converge relatively quickly. And so even after a modest number of iterations, we will get a measure of how important each vertex is. Any questions about that? Any questions about how PageRank works? And again, it works on there's a saying that says all roads lead to Rome. If all roads lead to Rome, then Rome must be an important place. PageRank is a good way to measure how important vertices are. They call it the centrality. I think centrality is, generally a notion of importance is like that. We once had a project where we took a look at Wikipedia, all the people that appeared in Wikipedia, and we wanted to figure out how important these people were. Okay, who's the most important person in Wikipedia? I'm in Wikipedia. Joe Biden is in Wikipedia. Is one of us more important than the other? The answer is yes. Okay, how would we figure that out? So one thing we did is we took the graph of all the pages in Wikipedia. Each vertex is going to represent a Wikipedia page. There will be a directed edge if they're from I to J, if page I points to page J. And when we computed the page rank on all of Wikipedia, now this was back about 10 years ago. So don't look for Donald Trump, don't look for Joe Biden. Okay? But who were the most important people in Wikipedia according to this, based on page rank? Almost all of these should be, if you look at them, I think you know all or almost all of the names here. Okay? Napoleon was the conqueror of Europe. George Bush was a president. Bill Clinton was a president. Obama was a president. You had a famous philosopher, Aristotle. You had the famous queen, another guy who tried to take over the world. Shakespeare, the greatest English writer. Jesus, the founder of Christianity. One of these names, I think, is surprising. According to this was the third, Carl Linnaeus was the third most important person as measured by Pagerank in all of Wikipedia. Who here knows who Carl Linnaeus was? Does anyone know who Linnaeus was? Why would the third most important person in the world be Linnaeus, in the history of the world, be Linnaeus, as measured by Wikipedia? Does anybody know who he is? Okay, when you took biology, you probably learned about the Linnaean Taxonomy. Carl Linnaeus was the one who sort of developed the formalism for how species are named. You've kind of, like what species do you belong to? Everyone here belongs to a species. What species are you? Human beings? No. Okay, you're a Homo sapien, right? Homo sapiens. And, I think if you're a Neanderthal, you're a something else, Homo troglodyte or something like that. Okay? So there's a classification system for every animal, plant, and microbe in existence, every organism. And it turned out that lots and lots of animals and plants and things like that have Wikipedia pages. And a lot of them were given their names by Linnaeus. Okay? And so every plant and animal pointed back to Linnaeus. That's why Linnaeus had such a high page rank. When we instead built a different graph, when we only consider edges between people pages, okay, suddenly Linnaeus is a lot less important because, not too many people point to Linnaeus, okay? A lot of animals do, okay? And they were important web pages. Any questions about that? In general, if you have a directed graph, finding the page rank of the items in that directed graph, okay, the page rank is a very useful feature for separating popular things from unpopular things. Now, in order to use PageRank in general, okay, in practice, there's a couple of things that you need to worry about. An important thing is to make sure you use the right graph. Here, notice we got quite different results, whether we had the graph of all Wikipedia pages or the graph of all people pages. Okay, the resulting importance of things often was similar, but not always. So it's important to have the right graph, okay? It's important to make sure that you, you get rid of, edges and vertices that are kind of either irrelevant or bad. As we said, if you wanted to increase your page rank, okay, if I have edges that go, let's say I have edges that go to, that were artificially added to me, okay, or there's edges that are irrelevant. They're either added in a hostile way, which is like spam, trying to fool Google into making sites seem more important than they are. But in general, editing out to make sure you have the vertices and edges that you want is important. What happens if you have a vertex, a Wikipedia page, where somebody points to this Wikipedia page But this Wikipedia page doesn't port to anybody. Okay, you could imagine a Wikipedia page that doesn't have a link to any other Wikipedia page, right? What's going to happen in a random walk on this page? What?
Like room.
Well, it's like, even though it may not have that many neighbors, but it's going to get a certain fraction of the power of all of its neighbors, but it's never going to let it go on the next iteration. Does everybody kind of see it? PageRank works on the fact that I start from where I am and I give my PageRank to other people. If I don't have any outgoing edges, okay, then I'm just going to keep accumulating PageRank and I'm going to get to be more important than I should be. So I should remove out the gray zero vertices. I should also not let my link to myself. Does everybody see that if in the Skinner Wikipedia page, we describe how great a guy Skinner is? I would now have an out the gray, but I'm going to keep all the mass that I had before. Okay, and I'd keep growing more and more powerful. The other thing that's kind of important is to avoid various other artifacts. Is often to make it work right, they usually have a dampening factor, meaning as you walk around the graph, with some probability, you're going to jump to a random location. This is good to make sure that you don't concentrate all the mass because of some kind of weird structure in the graph. One way Google does this, at least did it in the old days, was they added another vertex that they called God, that every vertex had an edge to God, and God had an edge to every vertex. This meant that from every node, there was a certain probability its mass was going to get transferred here, and in the next phase, transferred uniformly around the graph. Okay? And this had the effect of making it better. Okay? Any questions about that? So if you have a directed graph and you want to find out how important the vertices are, this is a useful thing to be able to do. You know, on Twitter, what would we expect if you ran Facebook, PageRank on Twitter? You would probably decide who is the most important, most influential person on Twitter, right? Because these are the people that are being followed by a lot of other important people. Any questions? Okay. One other kind of special algorithm on graphs that we're kind of loyal to is the idea of building what we would call graph embeddings. What is the issue here? If I have, let's say I'm Facebook, and I have the adjacency matrix of Facebook, there's maybe 6 billion people on Facebook. You could view Facebook as a sparse, but a 6 billion by 6 billion size matrix. Okay? You could view a feature vector for any one person on Facebook as being what other people are they connected to. But this is such a big, sparse graph, it's very hard to use this in an intelligent way to construct features as features. We'd like to take this giant network of connectivity. If we want to reduce that to features, we would like to be able to do something like SVD, something that comes up with a dense, representation, a d-dimensional representation for each vertex, where d is not that large, 50, 100, something like that. So that now every vertex can be viewed as a point in d-dimensional space. Okay? The good thing about doing SVD or any other matrix compression technique is that you can build a low-dimensional representation of the big matrix that captures most of the structure. Similar SVD vectors probably represent vertices with similar connectivity patterns. The trouble is SVD, or singular value decomposition, or PCA, or any of these other matrix compression things, kind of assume that you're working on a matrix. And so when you've got Mark Zuckerberg couldn't possibly build a 6 billion by 6 billion matrix because he didn't have enough storage to deal with it. And he couldn't possibly then run an n-cubed up algorithm like SVD on this thing. But there are techniques that can come up with small representations for vertices, okay, that are very, very useful, that we call graph embeddings, that are not based on matrix compression, but based on other ideas. One that we are very proud of, okay, is something we developed called Deep Walk, okay? And the idea here was that if I have two vertices that are very, very similar, have similar neighborhoods, they probably appear near each other on random walks. If I have an edge where I'm connected and all my friends are your friends, if we do a random walk from A, we're quite likely to discover B, okay, either directly or through, a friend we have in common or something like that. So a random walk on a graph kind of can be thought of as a sequence of vertices. A sequence of vertices can be thought of as like a sentence. So the techniques from natural language processing to build word embeddings, to tell you what words mean, those same techniques can be trained on random walks of data of a graph and come up with a representation for what each vertex is. Okay? And this is a good way to take normal network data and convert it to an embedding for each vertex that can work from the sparse representation of the graph, unlike traditional matrix methods. Any questions about that? So this ability to come up with an embedding for what a vertex means, okay, is a very, very useful thing. When we did this on Wikipedia, you can again imagine what is Wikipedia. In Wikipedia, you've got vertices representing web pages. You can represent edges from one page to another. John Lennon was invoked, okay, on the chat a few minutes ago. John Lennon was a Beatle, okay, he was a rock star, okay. When you do the deep walk on the people graph of all the people in Wikipedia, who was the nearest neighbor to Mick Jagger? Mick Jagger was not a Beatle, he was anyone know who Mick Jagger was? Or am I dating myself? He was a Rolling Stone. This meant that, okay. The fact that that this was a problem clearly means that I'm dating myself. Okay? But again, now once you come up with an embedding, every person in Wikipedia is a point in space. You can now come up with a distance function and tell me what are the 2 points in space that are nearest. And typically it's going to be points like it. The nearest neighbor to Beethoven was other classical composers. The nearest neighbors to Einstein were all physicists. Nearest neighbor to Scarlett Johansson were various actors and actresses of her era. Who was the nearest neighbor to me in Wikipedia? It turned out that Larry and Sergey, the founders of Google, were both my nearest neighbors. Now that's kind of amazing because 2 out of 3 of us are billionaires. Okay? Any questions about that? What's important? You see that the numbers here are the actual distance between the nodes. If you interpret that, what do we note about my distance to Larry and Sergey? Well, notice that, what do you notice about the distance between me and Larry and Sergey? They are, first of all, what it shows is the number here is larger than the nearest neighbors on these other domains, meaning I wasn't really that great a match for him, right? I was kind of a little bit hanging out in space, not that close to anybody else. The other thing to note is that my distance to Larry is almost exactly my distance to Sergey. What does that probably mean? If I am almost the same distance to Larry as I am to Sergey, what does that mean? Larry and Sergey have to be very, very close to each other, which is pretty what you would kind of expect. Okay? Any questions about that? So building these kind of embeddings are a useful thing, okay, as to kind of capture similarities of things. I think I encourage people to do that on at least one of the projects today. And any questions about that? I'd like to describe one other embedding method before I end, just because it's kind of a surprising idea and a very, very useful idea for coming up with representations of things. What if I wanted to come up with a really, really fast similarity between, let's say if I want, let me give you another idea for how you might be able to come up with an embedding for different, rows in an adjacency matrix. We agree, let's think that each of these are 3 different items here, and these are the rows in an adjacency matrix. Does everybody see that's one row? This is a second item that has a different row. This item is a different row. When you look at these rows, if you look at them, the first 2 rows are quite similar, right? The third row has a quite different neighborhood. How can I come up with a dimension, embedding, where I take this long n-dimensional vector and come up with a relatively short d-dimensional vector that is going to measure similarity? Well, what happens if I take a random, this is an n-dimensional vector. Suppose I take a random sequence of n random numbers and I do a dot product with this vector. And I take the same sequence of random numbers, okay, and dot it with each row. What happens when I take an n-dimensional vector and dot it with an n-dimensional vector? What do I get? I get one number, okay? Now what happens when I take a set of random numbers and dot it with 2 similar rows, the same random numbers, times 2 similar rows, okay? The dot product is going to do what? It's going to basically add up the terms in this random vector corresponding to where there were ones. What is going to be different between the dot product of the first 2 rows? If you look at these first 2 rows, in this case, they only differ by 1 element. Do you see that if I take a dot product against a random vector, it's quite likely that that dot product is going to be very, very similar between the 2 products. The only place where it's going to be different is the top dot product is going to have this number where the bottom number didn't, right? And so similar rows, when you dot them with the same random vector, are going to produce a similar dot product. Highly different rows are going to probably produce a substantially different dot product. If we take all the rows of our matrix and dot it with one particular random vector, this kind of defines a dimension. This defines a a one-dimensional representation of this, each row. If I now dot it with a different random vector, -3, 2, 1, 7, 2, 6, 1, 3, 5. If I dot it with a different random vector, all of them, I'm going to come up with a second dimension for my representation. And again, similar rows should have similar representations. If I do this d times, okay, by just doing a random projection of this matrix, I am going to come up with a d-dimensional vector for each row, okay, such that similar rows should have relatively similar vectors, okay? And this is a very fast, cheap way to do it. It's not as good as some of the other embedding methods, but it does kind of show you the power of randomness here. By picking independent random vectors, okay, we get different dimensions that should still capture similarity between things. Any questions about how those random dimensions work? In fact, this theory of random projections is actually kind of important. There's something called the Johnson-Lindenstrasse theorem that says if you have an n-dimensional vector, okay, and you dot it with log n squared random vectors, okay, then with high probability the closest points in if d is equal to log n squared, okay, with high probability the nearest neighbors in this compressed representation are going to be the same as the nearest neighbors in the full representation. Any questions about that? Any questions about graphs or graph data? Okay, nothing. Okay, I've got a few minutes left. I want to introduce, which we'll talk about next time, the other problem on graphs that turns out to be very important, which, as we talked about a few minutes ago, was associated with what you call connected components in graphs, which is that of clustering. Okay, clustering is a problem where we're trying to find structure in a data in a kind of unsupervised way. Okay, clustering, we want to try to assign groups to the items. Okay, labels. Okay, we're basically based on how similar they are. Okay, and I guess maybe I'll just start with this example, and then we'll resume next class. Clustering is the problem of taking points and seeing how many, and breaking them into groups. How many clusters of these points do you see? Here we have points, data in 2 dimensions. How many clusters do people see in this data set? You see 3. Does anybody see a different number? Nobody else sees 3? Some people tell me that they see 9 of them. Okay? Some people will tell me that you see 4 clusters here. One is an outside one. Do people see how you might see 9 clusters here? Okay? You might see something in between. Okay? Clustering is a ill-defined problem. Okay? But there is kind of natural structure here. Exactly what people call structure is probably different. Okay? Different people can come up with different impressions. Okay? It's not a well-defined problem. But it is kind of an important problem of taking items and grouping them, okay, into similar things such that we can describe a label to them. In the context of graphs, if we have a similarity graph, we saw that as connected clusters. Next class, we're going to talk more about this clustering idea. Any questions? Okay, any other questions about graphs, about projects, about anything? Okay, if not, thanks for your attention, and I will see you next class. Okay, we will talk more about clusters. Okay, thank you.